For this project, our objective is to create a model to answer the question, when is the best time to add an ice cube to coffee for the coldest coffee possible?
Our model can be looked at in two parts, the time before the ice is added and the time after the ice is added. Before the ice is added, our model considers the heat transfer between the coffee and air and the heat transfer between the ice and air. After the ice is added, our model considers the heat transfer between the coffee and air and the coffee and ice.
In our model, we made some simplifying assumptions, and these are what they are. After the ice cube is added to the coffee, it doesn't interact with the air, and the rate of heat transfer between the coffee and the ice is not dependent on the changing surface area of the ice cube. Some other things we considered were that the ice cube mass is 0.01 kilograms and the coffee mass is 0.2 kilograms, and these remain constant. All rates we picked are reasonably precise. The rates are dependent on the assumption that it takes about 30 minutes for an ice cube to melt in room temperature air, 30 minutes for a cup of coffee to drop from 90 degrees to 65 degrees Celsius, and 5 minutes for an ice cube to melt in hot coffee.
These graphs are results from a test simulation when ice is added at 17.5 minutes. As evident on the energy graphs, after that time, the shape of the graphs changed since the ice and coffee began to exchange heat. The temperature graphs reflect these heating patterns. The coffee temperature reflects the behavior of the energy graph fairly well, with the slope change at 17.5 minutes. The ice graph is a bit different since it undergoes a phase change as it heats up. To make our final model, we did this process several times, and each time we changed the time at which the ice cube was added to the coffee. At the end of each process, we took data from the last point on each of these graphs to compute the final temperature of the coffee.
The graph shows that the optimal time to put the ice in the coffee to cool it down is immediately after brewing, but there is a point around 17.5 minutes where the graph changes significantly. This point is where the ice doesn't have enough time to completely melt, so a portion of its low energy is not absorbed by the coffee, resulting in a hotter coffee by the 20-minute mark. While making this project, we also found that if we had an ice cube that took a lot longer to melt than a normal ice cube and a very insulated coffee cup, it would actually be more beneficial to add it in the middle of the simulation, which is apparent in this graph. This dip in the graph occurs because after this time, the ice cube doesn't have enough time to melt to be fully effective.